Okay. So today we're giving a little presentation on like design choices. You know, like last year we gave a talk on like how to make the PCB in the program, and this year we're gonna give a little talk on different properties of PCBs and like exactly what you want to choose, or what we're gonna go over like what we choose and the other options and why we choose what we choose. These are a list of a couple of things we're gonna go over. We're gonna go basically start from the beginning and go through all the testing and stuff. And then we're gonna go and at the end we're gonna go on the website we used, JLT PCB, and we're gonna buy a PCB that we've already made, and we'll see what that process looks like, because that's a little process that you can mess up pretty easily.
Alright, so the base material is that we use is FR4, and it's a kind of fiberglass material which provides flexibility and rigidity to the PCB. And it sits between and atop the copper layers, which makes it so that so we have in the middle we have a thicker slab of the material, and that's really what provides rigidity. And then between the copper layers, we have slightly between on the upper and lower halves, we could have this material to provide more of an insulation between the copper layers. And it's not yet. It's the most common type it's the most common type and it's found in most consumer electronics, and it's very cost effective compared to electronics.
Yeah. So yeah, this is basically the only one that we really use, because the other options are like using copper or aluminum, which is really good for like high heat, like high efficiency things, which we don't really we don't really use. So yeah, next slide we can go on to. So there's different like layers to your little board. So you can either have 2 layers, 4 layers. It basically goes in multiples of 2. So 2, 4, 6, 8. The more layers you get, the more options you have. So in this picture, it's actually a really good picture. We can see basically each of these we can consider like a copper layer. So they're all separated from each other, even though they look kind of connected. So what that allows you to do is if you have a lot of like signal and power wires going everywhere, you can, sometimes it's impossible to route that on a board unless you make it like really big. So this allows you to, instead of making it like bigger this way and this way, you can make it a little bit thicker this way and have something more compact, and allows you make something really complex like a computer like motherboard or something that requires thousands and thousands of connections fit in such a small space. Is actually not building this way but a little bit further this way. A side effect of that is improved heat dissipation. Like almost everyone should know, like the more material you have, the more heat will be absorbed by that material. And I mean, when you have more copper, it'll be better at heat dissipation, and that's basically like that acts like a heat sink for the board.
So single panel PCBs and so single PCBs would be individual circuit boards, and they're simpler. They're simpler for prototyping, and because you can kind of see where everything goes, and it's more laid out. Well, panel PCBs would be that one, and it's basically you print out multiple PCB boards on a single panel, and then you can just slot it and break it apart and then have multiple of the same thing, and it's more efficient for mass production of the material.
Yeah, and some when you manufacture some of these, just the PCB, it doesn't have any of the parts on it. So when you actually go and manufacture it, sometimes the pick and place machine will take something like this, but sometimes it'll also take something like this. A pick and place machine, for people that don't know, is just a machine that pick and places all the parts onto the board. And when you have it on something like this, like a panel, it can do 8 at once instead of 1 at a time, and that's obviously more efficient for mass production because there's less machine time. So when you get a panel like this, That's why it's efficient for mass production. It's because you can do 8 at a time instead of 1 at a time. So we obviously don't need to do this because we're not making like 10,000 a day or anything. We're making like 10 or 20 total. So we're going to go for something like this, but for someone that might want to mass produce something, it looks more something like this most of the time. So surface finish is something that happens pretty late into the process of the manufacturing, and that the surface finish can vary a lot. It's basically what helps you with putting on the components to your board. So the most common type and the one that we use is HASL, which stands for hot air level hot air solder leveling, and that and the second most common is ENIG, which is electroless nickel immersion gold. The difference between those two is HASL is extremely much cheaper, or not much cheaper, but eventually it adds up to be cheaper than ENIG, and it's very good. So when you're soldering, do you notice how your solder sticks to the pads very well over the random fiberglass that's around your piece? That's because of this final like surface finish. It basically makes it much easier for you guys to solder. So that's why we use the most common one, because it's like the cheap one. But if you use something like this, when you use something called solder paste, we'll go over that in a little bit, but when you're using solder paste, it's actually a little better for using solder paste because it's a lot smoother and flatter than HASL.
So copper has different weights associated with it, and it's measured in ounces per square foot. And based on, you choose your copper weight based on what performance you want to get out of this copper. And most common weights can be either 1 ounce per square foot, 2 or 4. And you would want, for example, to use 1 for more standard traces like the ones we mostly use. But if you would choose a higher weight, depending on if you want to pass more current, because the more copper, the more it can deal with these high currents sources.
Mm-hmm. Like for signal and stuff that requires very small amounts of electrons flowing through the copper, you're going to obviously want less weight. But if you're passing a large amount of power through something, you're going to want more copper, and you get to actually choose what you get to do when you're like on the website buying it. But like we use it changes per board, but we have a couple of boards. So we have like this one, for example, is like a power distribution board. It powers a computer, and we upped it to 1 ounce instead of 0.5, which we didn't actually put on the slide. But with 0.5 is like the signal, like the low current, and then we upped it to 1 ounce on this guy because we were dealing with more current, and we wanted some better heat dissipation, so we upped it. But if you're doing like big like power electronics, you're gonna go like 2 to 4 and stuff like that. Okay, so vias are like extremely important to, like when you're building a board. It allows you to do so much. Like without vias, it would be pretty much impossible to do anything more complex than like a logic gate. So a via is basically just a hole that goes through the board, like through the entire board. So in the design editor, it looks something like this. It's a little bit scary, but I promise it's not that bad. And the colors are different layers on the board. So red would be the top and blue would be like the bottom. And the reason why we use vias is because when we are routing around, if you notice, sometimes we need things to go under each other, right? So we start here and we have to go under and over traces. So for example, if we look at this trace right here, we have to go over this blue, but under this red. So we can't really, like, there's no way to do that without changing sides, right? So we use the via which kind of looks like this. It's a little bit of a, it's not the greatest drawing, but it's basically just a little hole filled with copper that goes to the other side, and you can tap into that from any layer. So remember how we talked about different layers, amounts like 4 layers, 8 layers. A via goes through all the layers to the other side, and you can kind of tap into it like a faucet in different places, like a little, like if I wanted to tap it onto layer 6, I can go and tap into it, and the same would work on layer 2 and layer 5, whatever. It doesn't really matter where you tap into it, but it basically just extends it so you can basically go on wherever you want. And that's kind of what these are for, and that's what allows you to really do a lot of crazy things on boards. And there's different like via coverings, and they have different properties. Scott, can you go over that a little bit?
Let's see. So I think this your picture is kind of explaining things that are bad about tented vias. Anyway, so there's the question of whether with the vias you can either not tent them at all and basically leave them, have copper exposed, the holes all the way exposed. Allows you to use it for like soldering wires into it or probing it with taking meter probes and poking them into the holes. With the tented vias, it completely covers the via, and it ends up what this is explaining is that can cause issues of entrapping air, solvents, air, debris, so that when it ends up heating up or something, it can end up causing damage to the circuitry. But it also makes it where the via isn't exposed to having debris getting into it. So there's kind of a benefit there. It's kind of a trade that you have to work. Beyond that, I think. There's another way of handling it when you fill vias. They kind of fill it with an epoxy. After building the board, they'll fill the vias with epoxy in order to kind of make it where it's in some ways better than the tenting approach, where it's not, because you can end up keeping material from getting into there. But anyway, I think that's about it.
Yeah. So I believe we use the partially tented option.
Yeah.
Because of the negative side effects of all
exactly.
the rest of the 4. Yeah. Do you want me to do this one? Okay, so the flying probe test happens at pretty much the end of the manufacturing of this board. And what that does is there's these little probes, like they look a little scary, but they're pretty helpful. So it's one of the tests that they do before they give it to you. And it uses these little test probes that jab at basically every point in the board. And what it does is it quickly tests continuity between 2 points on the board. And it just does that thousands and thousands of times. And it's very easy to set up because it doesn't go randomly, but it kind of just goes around and tests the same thing every time. But it doesn't test for other things that you like. It doesn't test for other things that it doesn't test for everything. It only tests for the continuity between points. And because it only has these probes, you need bigger and different machinery to do other tests. But it's very easy to set up. It's good for doing things. It takes a little while. So if you're ordering like 80,000 of something, it's probably not going to work. But it works for, like, our boards go through it and stuff like that. And but if you had something like you're a mass manufacturing something, like you would have to do something else. So yeah.
Okay, so PCB color and silkscreen, you'll see that most PCBs, when someone thinks of a PCB, they mostly think of the green PCB, which is kind of the standard color. But PCB manufacturers do have a lot of different colors that are available. And you'll see that we do use some black PCB because it's our color. But some of them are green because that's the standard. And the importance of silkscreen, which is the actual text on the board.
Yeah,
like you'll see our design here, and you'll see just text in lines. As is how you point out if someone is to look at your board for the first time, like they aren't the person who designed the board, you want them to know where you want power to go in or where you want signal wires to go in, and that's what you denote with the silkscreen. But also, if you produce your connector, your PCBs in-house, like you manually solder stuff on, you want to know, does this component, where does this go? And you denote that by our little tags. We have little white tags next to each connector.
Yeah, so for example, this goes on the little reel, so everyone has one of these. So we have encoder 1, encoder 2, digital input, and the arrow denotes pin 1 and stuff like that. I'll show everyone. But the different marks, that's all the silkscreen on the board. So pin 1, the label. And on other boards, this board doesn't have it, but when you're doing actually you can pass that around. When you're doing when you're doing more complex boards with a bunch of different components like resistors and stuff, you'll put what's called a reference designator, which is a little number R37, and what that'll denote to, like that. What it'll denote to is a part that you bought. So let's say, we have boards with up to like 30 or 40 different individual components, like one of these. Yeah, you can pass that around. And the way we figure out where everything goes is we give it a reference designator, Zach pointed out right here, and that lets us, when we're manufacturing it, because we pick and place it ourselves. So we have students go and actually put, on that board, a student placed all those parts. It wasn't a machine or anything. The only way we can figure that out is by using these silkscreen, these laser printed marks, and to figure out where parts go and what orientation parts go, because sometimes parts have a little problem. So this dot, for example, denote pin 1, and that matters a lot because when you're doing things when you're interacting with devices that aren't yours, like that goes on a computer, like a very similar. It's like a Raspberry Pi copy, and the only way to figure out where to move move around traces is to actually know where your pin 1 is and where things are going. So with that knowledge, you can do a lot, and that's why we put on these little marks. It's a little different for things that are mass manufactured and use machines, because sometimes they don't really need the reference designators. They have fiducials, which are almost like April tags, or QR codes, that allow them to figure out where things are. But other than that, if you're in FRC, it'd be you're picking and placing them yourself. You're not going to buy them most likely.
Also, the part itself would have a denoter for pin 1, but you can also see here, this also has a special characteristic that it's square rather than circular, and that is often used also to denote a pin 1.
Okay, we'll move on.
So stencils, this would be what a stencil is, and it's a template. If you see these little holes, for solder paste, applying the solder paste. So you take one of these raw boards, which actually matches this one. You place it, you'd place it under, and then you would line up the holes with each other, because you'll see there's these little shiny pads. You want to get solder on these. So this will help you line it up. Then you take
some paste,
and you scrape it along here, trying to get it perfectly on the holes and not too caked up on top. You want to get it perfectly the thickness of this material right here, which actually can matter for certain components, because you don't want if it's too caked up and you have some tiny little pads right super close to each other, you don't want these to overlap and short your circuits. And it's critical for surface mounting, because you'll see typical electrolytic capacitors, which are the cylindrical ones that you put through the board. There's some surface mount ones. You wouldn't need the solder paste because they're through holes, so you can hand solder them without having to apply paste. And
Oh yeah, so there's different like ways you make the stencil. They don't. I guess they don't really matter to us that much. But when you're doing like for example, I believe we use electro polishing for like the like how we get the sorry no not electro polishing. We use the laser cut. And we use that. I believe the chemical etched version is a little bit better, but we only use the laser cut one because we don't need really small holes. I think.
It all depends on what tolerances you need for your components and whatnot.
Yeah. Actually, we can just pass this around too.
Yeah. Wait, I'll also pass it with this.
Okay. Yeah.
This is the board. This way.
So yeah, so when you're like making things that aren't like typically a lot of people's soldering experiences with things that go through the holes, through the PC, like through the whole PCB, the vast majority of components you use, like the industry uses are not actually through hole. They're just on one side of the board and they're a lot smaller, like very small.
Also, each side has the reason why there's two different things is that you have to do one for each side.
Yeah.
So you'd have to apply paste, put your components on, reflow, and then flip it over and then re-stencil for the other side.
If you want to like hand like mount surface mounted devices without using like a pick and place, like how would you do that?
Oh yeah, you got.
His question was, if you were to surface mount components without a pick and place machine, do it like at home, like we do, you would have to, like my answer to that would be that you would have to take tweezers and like pick up the components, like you'd have like taped components or roll, but roll is for like mass production. So you have components in like this little strip of things, and you pull out the component with tweezers, and then once you've stenciled it, right? So there's already paste underneath. You have to place the component on the paste and make sure that you don't smear the paste or short stuff together or whatnot. And then from there, you would put it in what's called a reflow oven, and you would basically cook it until the solder melts. So it's a pretty high temperature because soldering irons, they get pretty hot. It's right there, actually.
Oh yeah.
So you can see this is a kit that we bought for some amount of money, and it comes with these programs, and basically it's like, this is like a like hand oven or whatnot.
It's like a little like toaster.
Toaster oven. So we take a raw board, we've stenciled it, and we've hand placed the components on it. We put it in here, we just close it up, and then this isn't powered on, but there's a little computer, and then we just type in, there's like a preset, we say go, and then it gets it to a certain temperature, keeps it level for a little bit of time, then actually spikes all the way to melting temperature, I guess.
Yeah.
And keeps it there for a bit, and then it opens up, like there's a little servo here, it opens up and it helps cool it down for a little bit, just with room temperature. So we'd rather not do it indoors because there's fire alarms, but
We set them off
and
before.
don't breathe solder fumes, but you just do this, you get it out, and then now you'd have to do the other side, stencil it, place your other side components on, and then because there's now like extra height to the board, which might not be equally distributed, we've had this problem with this board actually, you might have to place like other stuff underneath it.
There's some in the toaster.
Oh yeah, there's our dummy boards. Yeah. So these are just boards that weren't correct, right?
Yeah.
So
we'll stand up.
We'll put them in the oven and then stand them up, and just keep headroom for whatever components are poking out on the other side.
So yeah, the board will go in twice. It'll go in once, facing upwards or downwards, whichever one we decide. Typically, for boards like this, the bottom's way simpler, so we start on the bottom and then go up.
Yeah.
Also, certain parts can only get reflowed once or twice.
Mm-hmm.
And so you need to figure out which side to put all the
Which
parts
side is
on.
more sensitive and whatnot. It'll usually be described. Just leave it there.
Thank you.
And yeah, so From there, you would have to hand solder whatever components need to be hand soldered. You don't hand solder before. Well, you could, but that would be painful. Actually, one of our problems with this one was that we were afraid that one of the larger capacitors would fall off if we had it, because it's kind of heavy and it might just plop down. It didn't end up doing so, but it would have been a possibility, and it's pretty big, so we would just re-hand soldered it if that were the case.
Yes. Okay. So this is what. Oh, sorry. This is what the little site looks like for purchasing. There's a lot of, like, remember how we talked about base material, layer count, thickness. We didn't really talk about, but we did talk about color, silkscreen. This is all on the site. So.
How do you submit the?
Oh yeah,
Yeah. How do you
yeah.
file, how does it know what file to use?
Okay, so I kind of hid that part. So, so we have this thing. Oops.
Yeah, show my.
My bad. I'm flashing your downloads, man. Okay, so we have this. We generate this from the program, which I showed in the last presentation. I'm not gonna go over it again because it'll take a little bit of time, but. You can, once you made your board, you generate these files, which are called Gerbers. I don't know why they're called that, but they're called Gerbers, and they're basically just the files that are universally understood by manufacturers. So no matter what program you use to design your board, you can go ahead and generate Gerbers, and it'll be universally understood by, I'm assuming, almost every manufacturer around the world. So we actually have his program's being a little weird, but we have a little you can generate a little bit of a few PDFs that I'll show because the program isn't working. But like for example, these are the holes that, like, the big holes we're cutting. So for example, there's like a little legend at the bottom. So these are the size of the holes. We have the X's are these 3.7 millimeter holes. So these massive 3.7 millimeter holes in the corner. You want to pass around that?
Yeah. So basically, there's a hole here, and then there's connecting holes here, and I'll pass this around so you can.
So yeah, that's a little bit bigger than these two holes, and so that's called the drill map, or the DRL map. And then we have, where is it?
Just scroll up.
Yo, where is it? All right, found it. Okay, and then we have, I don't know if there's a difference between these two. Oh yes, there is. Okay, so this is another drill map that we have. So
The first one were the holes that were not plated.
yeah, oh yeah.
These are plated holes.
So the other ones were holes that are literally just holes. Like you can literally take a drill and just drill.
Well.
Well, you could do that to make that hole. We don't do it, but you could do it if you wanted. These are.
You don't want to short copper layers together and stuff.
These are actually the holes that have copper in them. So, like, for example, all of these X's, these tiny X's, are, remember when we talked about vias? These are all the vias. So remember we had those vias down here we were showing you? And then we have these rectangular ones, which are the connectors on the board. So if you see, like, the two connectors that are near the plastic edges, those are these guys. And then we have the button, which I believe is these pluses. So the different symbols just mean different sizes.
You'll see the legend down there.
Yeah, there's a little legend. This is for the battery holder. That holds a little, like, battery in the middle. We'll show you how that works at the end because it looks kind of weird, but. And then this is just a rotary switch. So it's a little. You probably have something in your car. Actually, you probably have that in your car somewhere if you have a car. Odds are. And yeah, so there's a bunch of different plated holes that you can basically make any shape you want. Like that's a kind of weird shape, but you can like make it like ovals. You can make rectangles. You can make pretty much whatever you want, like shape wise for these holes. So yeah, that's pretty cool. So then you import that into this program. Yeah, actually I can do it again. So here, this is like just like the home page. Like there's no like add video URL. This is the home page. But you basically just add, it generates it for you. It generates the zip file for you, and you just import. Upload failed. Okay. Okay, man.
Okay.
So, oh, I know what I did last time. No, go to instant quote. Okay.
Oh.
Maybe it just needs to work from here. Okay. Okay. Well, whatever. You choose. You can just get a quote or make an account number. You put in the zip file, and it does all the work for you. There you go. And that's the board that you have that you were passing around. So.
There are different materials.
Yeah. Oh yeah. There's some cool materials that we can go over actually. So you can actually make flexible PCBs. That you can basically make a cable, like a little like you could if you wanted to, you could make like if you wanted to connect two boards, like two different boards, you could make a flexible PCB that like bends around and connects it. So I'm trying to think of examples. I can't think of any right now, but
Like the
Kinda
MIPI
like
cables.
MIPI cables.
oh yeah, I don't know if any of you guys have worked with camera cables before, but there's these like little like cables, and they're made of this material. That's a MIPI cable. So it just goes into your camera. If you ever work with a Raspberry Pi camera, you work with that. If not, that's what you work with if you ever work with a Raspberry Pi cable. A camera cable. Doesn't have to be a Raspberry Pi. Okay. And then there's like aluminum. They give a little summary actually at the bottom too. So you use these for something okay, so like for example, these aluminum PCBs are not universally in the United States are used for stoplights. So that's why like it's something very good for lasting a really long time, and it's like basically it's like perfect for LEDs, and that's what your traffic lights are. Copper core is actually quite similar.
No description.
I guess there's no description. It's something like it's like if you're it's like high power, like high current, like you have a lot of heat. You know things are gonna get hot. You don't like coppers, like that's what heat sinks are made of, right? So you have your board, and it's basically made of a heat sink, and it's also it's basically good for the same thing as aluminum. It's just copper, and also the reason why we don't just like copper aluminum, that's a good crazy, like that's so good. Like why don't you use it? It's because it's more expensive, and we don't it's enough even here if we change it. See, now it's $46.
It was $2.
It was $2 before. So we're not about to break the bank, you know, like let's just go with fiberglass. Like we don't need that. Like we're good. Okay, let's continue. So layers. It automatically detects how many layers it has because it's a property in the Gerber files. So this is a 2-layer board because it's not very complex. Like it's a very simple board. So I designed this board. But like the board we passed around beforehand, the one with that connects the computer, that board is a 4-layer board because it has more to go on. But at his work, he showed us a couple boards that are 8 layers and 14 layers.
So that's the price.
Yeah. Oh yeah. More layers is more price, obviously, because it's more material. But yeah. And then it defines dimensions for you. You can define the quantity. If you change this, what happens is the testing rigor increases. So if you do aerospace, it's gonna increase it. It'll add. I think I don't know what test it adds, but okay, the 4-wire Kelvin test, and then the medical test will, I believe, be the same thing. Yeah. But it'll add a layer of testing, which will cost a little more. But I believe there's some regulations where you need to do that. Different design is only if you you have 3 different designs you want to build at the same time, and you can go and change that. You can upload more designs. Okay, remember how we talked about single PCB versus panel PCBs? So you can do panel by customer, and you basically can define how wide and long you have. So let's say your machine can only take a certain length and width or whatever. You can decide that.
panel by JLC, I believe, it does something a little different, but I would suggest, I've played around with panel by customer, and that one seems to work the best. PCB thickness, we don't really have to go over. PCB color, just keep it default. PCB color, you can change the color, and then voila, it changes. We like black. I mean, the only side effect is it takes 2 more days than green, but if you're not in a rush, then you can change the color, and it's free of cost. So like the cost doesn't change for color.
It's just because they already have the material, but they have to swap the machines and like swap it into the machines and whatnot, and it just takes more time for them.
And then remember how we went over copper weight, or outer copper weight and inner copper weight is outer copper weight. We remember how we defined like 1 ounce or 2 ounce for like more high power electronics versus lower power electronics. For this board, it's just like signal, and it's very small amounts of power because it's like a little 3-volt battery. So we're gonna go with 1 ounce. And the via covering, we've always used tinted. So and we went over the other ones, and they all had side effects that we don't like. So we always go with tinted. Confirmed production file is like if you want some representative there to look at it. If you're really not comfortable with if it's your first thing, I would suggest saying yes, because they'll go, and if they see you made a little small mistake, that'll cost you a lot of money, because they're just gonna send it to you. There's no like warranty or anything. Like they made it, they can't get the material back. So I would say yes if it's like your first board and you don't know what you're doing. For me, it wasn't, so I did no. Order number, whatever, doesn't matter. Flying probe test was, remember we went over that little test with the little probes that. So the flying probe test will happen, so it'll see if your the manufacturing process was messed up or not. Gold fingers is if you're doing something like if you've ever put in like a GPU into a computer, or have like a piece of RAM in your hand. If you notice the fingers are pretty shiny, that's because they're gold plated. And you can do that if you have an application like that. All these are the same. And then we went over the stencil. The stencil that we showed to you guys, we used a framework, which is just the frame around it, which is easier to hold. So if you're gonna get a stencil, when you get a stencil, get a one with the frame, because you need to hold it down very well, because you don't want to mess up. Everything else we keep the same, besides so there's different polishing processes you can use. So if you have very small pads, you're gonna want to go to like electro polishing instead of sanding, because as most of you might know, sanding will still be pretty rough when you're done. So electro polishing will get very, very sharp, and it'll be very very clean when you put on the paste. So we go with electro polishing. For this board, we don't have to, because there's no small parts. But for a board with smaller parts, like also the one we passed around, you're gonna want to use electro polishing. And yeah, basically, it's not actually very hard to order a board. You just need to know what the terms mean, because otherwise it's a little scary. Any questions? There are no bad questions. Yes.
Apart from the reel, where else do you guys use PCBs on the bottom?
Okay, the question was, apart from the Robo Rio, where do we use PCBs? And my answer is, where do we not use PCBs? In 2022, our 2022 season, about more than half of our losses was because of connector issues. So we would lose connections to all of our sensors really often, and our robot would not work. So we were like, in 2023 we were like, or 2022 we were like, summer 2022 we were like, we have to fix this. Like, what can we do to fix this? And Scott was like, you know what you do? We just make a bunch of connector boards. So we went and we made 5 boards that interact with all of our sensors, and so all of our sensors are connectorized. So we don't have any with us, but you can pass these around.
You've got one board back there that's sort of.
Oh yeah, we do. Okay, so this one So we use these, let me pass these around too. These go on to potentiometers, which are these little, these little like shafts that spin, and the resistance changes. So it goes from 0 to 1,000, which is the one we use, and that gives you a position, like an absolute position of where we are. And the problem with those sensors is you have to solder directly onto them. And the problem we would have is when we would have to, that solder connection would break off very often. So you're like, let's have a board that solders directly onto it, which will be significantly stronger and it'll be permanent, and it turns it into a connector. Then we use mag encoders, which I bet a bunch of you guys have used before, which are like these little magnets that attach to shafts that spin, and that comes out as a really, really bad ribbon cable, like really, really small cable. And we made a board that eliminated the problem of that ribbon cable almost entirely. We made boards for our encoders that connect to our like our drivetrain wheels, which gives us the speed of the wheels. We created boards to interact with computers, like Raspberry Pis, that allow us to drive our cameras. And we made a board for our IMU, which stands for Inertial Measurement Unit. It's a fancy term for an accelerometer and a gyroscope that allows you, when you don't have vision, to figure out where you are on the field. So a lot of our boards are based on robot localization, which this is a fancy word for where am I on the field, like where am I and when am I on the field. And a lot of our boards are for expanding our connectors so that when we get hit by an 125-pound robot at 15 miles an hour into a wall, nothing unplugs. And that's what we did. Does that answer your question? Yeah. Any other questions? Aaron.
What are the benefits of making the boards in-house rather than having the factory make them?
His question was, what are the benefits of making them in-house versus in the factory? So in the factory, I actually tried the other day or a couple weeks ago to get one from the factory to eliminate the need for human labor. Unfortunately, they screwed up really badly, and it was a really easy board. They somehow messed up a really easy board. But another one of the things, which is a negative, not because of because it's a negative because if you make them in the factory, then the people don't learn. So, like when I had a bunch of people making them, they would always ask questions, and once you start asking questions, you start learning. So when you make them in house, you first of all you learn how annoying it is to make it, but it's also really fun. And you get really good hand-eye coordination. Like, holy moly! Like, if you want to be a surgeon, if you want to train for being a surgeon, go ahead and try it, man. Like, if you have shaky hands, like, you'll learn how to have less shaky hands. Trust me, my hands were really shaky, and now
millimeter tolerances.
Yeah, millimeter tolerances. You learn I don't know. It's really you bond with everybody. It's really fun, and you also learn a lot about what you're doing. And you also mess up, and you get really mad, but then you fix it, and it's really fun. Yeah. So the advantages of in-house is it's fun most of the time, and you learn a lot, and you bond with everybody. The negatives is you need humans, and sometimes teams don't have humans, and that's life. And
Team made of robots.
Team made of robots, yeah. It's it's obviously going to be, if you figure out how to do it right, it'll have no problems if you figure out how to get it shipped out from a board house. But it pretty much, unless you want it to cost you $1,000, you have to get it from China, and that takes a while. The turnaround was 10 days or 20 days.
Also, one good thing of ordering or making them in-house is when you buy the boards themselves, they come pretty cheap, so you can buy 100 of them at a time. And then from there, the most expensive part is the components you put on top. So you can buy 100 boards one year, but only build 5 of them this year. And then depending on the prices or whatnot, you can buy if you run through 5 in a year, right? You'll have to make 5 for the next year, and then you just order the components. You don't have to tell the manufacturers just build it for me now, right? Because you won't know how many you need.
All right. Thanks, guys, for listening.
Yeah, thank you.